Welcome to the Watchdog Timer WDT chapter of the HT32 MCU basic tutorial. This tutorial will introduce to you the HT32 MCU WDT function. We'll introduce this function from four aspects: WDT Overview, WDT Structure, WDT Registers and Programs, and WDT Application Example. The first section is WDT Overview. In this section, we will learn about the basic knowledge of the WDT and the features of the HT32 WDT. The following is some WDT basic knowledge. First, we'll briefly introduce the WDT. Essentially, the WDT is a hardware timer that can generate a system reset signal. During normal operation, the counter value must be refreshed before it reaches zero, that is, the counter must be reloaded. This process is commonly known as feeding the dog. When an error occurs and the feeding the dog program cannot be executed, the WDT will reset the system. Unlike general-purpose timers, the WDT is not suitable for handling routine tasks. The primary purpose of enabling the WDT should be to reset the system. Next, talk about the WDT applications. The WDT is a critical component for ensuring the system's stable operation. It can be used in many applications, such as industrial automation control systems, IoT devices, medical electronic devices, and automotive electronics. The WDT can respond quickly when the system occurs unexpected events or failures, restoring normal operation via an automatic reset. This reduces downtime and the economic losses caused by system failures. It plays a vital role. Whether to enable WDT should be determined by considering factors, such as the application's specific requirements, the operating environment, and the importance. It is recommended to enable the WDT to enhance system stability and reliability. The HT32 MCUs integrate a watchdog timer function, which is mainly used to prevent program crashes and monitor program operation status, thereby effectively improving system stability and reliability. The HT32 WDT features are as follows. The independent clock source can be supplied by either the internal 32 kHz RC oscillator, LSI, or the external 32.768 kHz oscillator, LSE. It is unaffected by the main system clock. Supports a programmable timing function. The watchdog timer includes a 3-bit prescaler and a 12-bit countdown counter, enabling user to set the WDT timing. Supports a timeout reset function. When the WDT counter reaches the preset value or times out, a reset signal will be generated to reset the system. The largest timeout period is 16 seconds. A limited reload window function is used to custom WDT reload time within the window time. This prevents the counter from being reloaded improperly or triggering a software deadlock. The counter can be set up to stop counting when the system enters the sleep mode. The WDT provides reload lock and configuration register write protection functions. Note that the LSI clock source of the watchdog timer is subject to drift depending on the operating temperature and conditions. This results in the WDT timing not being absolutely accurate. The second section is WDT Structure. In this section, we will learn about the WDT internal structure. Then, we'll briefly introduce the WDT block diagram. The WDT clock comes from either the LSI or the LSE. A 12-bit down counter clock is obtained by dividing CK-WDT by a 3-bit prescaler. When the WDT is enabled, the counter reloads the WDTV value and counts down from this value. The WDT ERR and WDT UF flags in the WDT SR register will be set respectively when the watchdog timer error occurs or when a watchdog timer underflows. If the WDT RSTEN bit is enabled, a reset signal will be generated to reset the system. During the WDT counter counts down, if the counter value is less than or equal to WDTD, reloading the counter value, that is, feeding the dog, will not generate a reset signal. If the counter value is greater than WDTD, reloading the counter value will cause a WDT error and generate a reset signal. The following WDT timing formula is provided for reference only. Note that the watchdog timer uses two clocks, PCLK and CKWDT. The PCLK clock is used for APB access to the watchdog registers. The CKWDT clock is used for the watchdog timer functionality and counting. Then, let's go on to the WDT reload and reset behaviors. When the WDT counter counts down from the WDTV value, if the counter value is less than or equal to the WDTD value and a reload operation is executed, no reset signal will be generated. If the counter is not reloaded in time, it will underflow. If the reset function is enabled, a reset will occur and the counter value will be set to FFF hex. If the reset function is disabled, no reset will occur and the counter value will be the WDTV value. If the counter value is greater than the WDTD value and a reload operation is executed, a WDT error will occur. If the reset function is enabled, a reset will occur and the counter value will be set to FFF hex. If the reset function is disabled, no reset will occur and the counter value will be the WDTV value. The third section is about WDT registers and programs. In this section, we will learn about the relevant WDT registers, program description and how to enable the WDT. Then, we'll briefly introduce the WDT-related registers. The first register is the Watchdog Timer Control Register, WDTCR. The RSKEY bits are the reload lock key, and the WDTRS bit is the watchdog timer reload bit. Set the WDTRS bit to 1, and set the RSKEY bits to 5FA0 hex, the WDT reload function can be enabled, and the counter will be reloaded with a WDTV value. The second register is the Watchdog Timer Mode Register 0, WDTMR0. The WDT-EN bit is the WDT running enable bit. When the WDT-EN bit is set high, the WDT will be reloaded within the WDTV value and count down. The WDT-SHLT bits are the sleep halt configuration bits for the watchdog timer. The watchdog timer stops counting when the WDT-SHLT bits are set in the sleep mode or deep sleep mode 1. The counter value is retained, so that it continues counting after the system is woken up from the sleep mode or deep sleep mode 1. The WDT RSTEN bit is the WDT reset enable bit. When the WDT RSTEN bit is set high, a watchdog underflow or error will trigger a system reset. The WDTV bits define the reload value of the WDT 12-bit down counter. Note that the watchdog timer always halts when the system is in deep sleep mode 2. In addition, when the system enters the debug mode, the watchdog timer counter will either continue to count or stop depending on the DBWDT bit in the MCU DBGCR register in the clock control unit. The third register is the Watchdog Timer Mode Register 1, WDTMR1. The WPSC bits are used to selection the watchdog timer 3-bit prescaler. The WDTD bits are the watchdog timer delta value, which are used to define the permitted range to reload the counter, that is, the counter should be reloaded again within the delta value. Note that if the counter value is greater than the delta value and a reload operation is executed, a watchdog timer error will occur. The fourth register is the Watchdog Timer Statue Register, WDT-SR. If the WDT ERR is set high, this indicates that a watchdog timer error has occurred. If the WDT UF bit is set high, this indicates that a watchdog timer underflow has occurred. The fifth register is the Watchdog Timer Protection Register, WDT-PR. The protect bits are used to enable or disable the watchdog timer configuration register write protection function, except for the WDT-CR and WDT-PR registers. The sixth register is the Watchdog Timer Clock Selection Register, WDT-CSR. The WDT lock bit is used to configure the watchdog timer lock mode. Software can set this bit to 1 at any time. When the WDT lock bit is set, the function and registers of the watchdog timer cannot be modified or disabled, including the watchdog timer clock source, and only waits for a system reset to disable the lock mode. The WDT SRC bit is used to select the watchdog timer clock source. The watchdog timer monitors the system status using the timer mechanism. If an abnormality is detected, the watchdog timer can respond quickly by executing a system reset, effectively preventing the system from crashing or entering an error state due to a fault. This improves the system stability and reliability. The watchdog timer plays a key role in ensuring the stable operation of the embedded system. The following will introduce several WDT-related functions. The first function is used to enable or disable the watchdog timer function. The second function is used to configure the watchdog timer sleep halt. The third function is used to enable or disable the watchdog timer system reset function. The fourth function is used to enable or disable the watchdog timer register protection function. The fifth function is used to set the watchdog timer reload value. The sixth function is used to set the watchdog timer delta value. The seventh function is used to set the watchdog timer clock prescaler value. The eighth function is used to feed the dog or reload the watchdog timer counter. The ninth function is used to get the specified watchdog timer flag status. The 10th function is used to enable or disable the watchdog timer lock mode. The 11th function is used to configure the watchdog timer clock source. We will then introduce two methods to enable the watchdog timer in an actual application. The first method uses the HT32 code config to enable and configure the watchdog timer. Set the WDT clock source on the clock configuration page, then switch to the timer page and set the WDT parameters in the WDT column. The second method uses the System Wizard mode to enable and configure the watchdog timer. Open the system_F5xxxx_01.c file in the Keel project, then switch to Wizard mode. Configure the WDT parameters in the WDT column. The above two methods are used to enable the watchdog timer easily. Finally, we'll provide an application example to summarize this tutorial. This example is taken from the WDT period reload program in the HT32 standard firmware library. It should be used with the hardware HT32F52352 starter kit and ESK32-2X001A expansion board. In this experiment, LED 1 and LED 2 flash alternately at a period of 100 milliseconds for around 8 seconds. After this, turn on LED 1 and turn off LED 2. The program flow is as follows. First, the system initializes the LEDs and configures the SysTick timer and the watchdog timer. Then, it continuously checks the WDT status flag within 8 seconds of WDT startup. During this period, the SysTick timer responds to an interrupt every 100 milliseconds, changing the LED 1 and LED 2 statuses within the interrupt service function. After approximately 8 seconds, the WDT counter will underflow by default. After this, disable the SysTick timer interrupt, turn on LED 1, and turn off LED 2. The program enters a loop and waits. Here are critical codes of this example. The first step is to initialize LED 1 and LED 2 configuration. The second step is to configure SysTick tick timer. The third step is to configure the watchdog timer. After the above configuration has been completed, the program enters an infinite loop. First, check the WDT counter underflow flag. If a counter underflow has occurred, disable the SysTick tick timer interrupt and control the relevant LEDs. The program will then enter an empty loop. Otherwise, go to the next judgment. Then, check the watchdog timer error flag. If a watchdog timer error has occurred, disable the SysTick tick timer interrupt and control the relevant LEDs. The program will then enter an empty loop. Otherwise, end the judgment of this round. If no flag is set high, the program will repeat the above program until the relevant flag bit is set high. That concludes the tutorial. Holtec has a professional service team to assist in the development, design, and after-sales service. Welcome to contact our business unit for more detailed product information and consulting services.